Hello and welcome to today's webinar, Converge for Hydrogen Combustion Modeling, Transportation, Aerospace, and Safety, brought to you by Convergent Science and Wabtec. Thank you for joining us today for this new installment of our webinar series. My name is Scott Davis and I'm part of the business development team at Convergent Science. I'll be your host for today's event. We're excited to showcase Converge CFD software and its capabilities in hydrogen combustion modeling. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. We'd also like to welcome Wabtec. Wabtec is a leading global provider of equipment systems, digital solutions, and value-added services for the freight rail, transit, mining, industrial, and marine industries. Thanks for joining us today. And if you have questions during today's webinar, please use the toolbar from GoToWebinar and use the Ask a Question feature to submit those questions. We'll spend time at the conclusion of the webinar answering some of those questions. Today, we have two presenters. First, we will hear from Dr. Sameera Wijeyakulasuriya. And Sameera has been with Convergent Science for over 12 years. He is currently working as a project manager leading the internal combustion engine application support team and is a key resource for Converge support globally. Sameera received his PhD in mechanical engineering from Purdue University and currently resides in Madison, Wisconsin. After Sameera's presentation, we will hear from Dr. Adam Klingbeil. Dr. Adam Klingbeil is an engineering technical leader at Wabtec. He received his master's degree from the University of Wisconsin-Madison and his PhD from Stanford University. Dr. Klingbeil has contributed more than 15 conference and journal publications and is co-inventor on over 60 patents. With 16 years of experience in large engine testing and combustion system optimization for low emissions and improved fuel efficiency, Dr. Klingbeil has helped to develop key performance technologies used in Wabtec's Tier 3, Tier 4, and next fuel in locomotives. The time is now yours, Sameera.
Thank you, Scott. So as Scott said, my name is Sameera Wijeyakulasuriya. I'm a project manager at Convergent Science. Today, this webinar is going to be of two parts. I'm going to go first and talk about the challenges with hydrogen combustion and storage, and how with Converge you can overcome those challenges. And after me, Adam from Wabtec is going to talk about how they use Converge in their CFD analysis of a large bore hydrogen diesel dual fuel engine. After Adam's talk, we'll actually open up the session for questions and answers. So now first actually look at what are some of the engine design challenges with hydrogen as a fuel. One of the first things is like flame flashback or backfiring. These relevant in port fuel injection engines, where you have a fuel coming in from the intake port and flame in the combustion in the cylinder could actually jump into the intake port, and we want to avoid that. These also can be seen in gas turbine engines and burners, as you can see on the video that is playing. It's a hydrogen and methane fuel swirl burner, and you can see under certain conditions the flame would actually go back in towards the swirler, which should be avoided. Now, with hydrogen PFI engines, compared to their diesel counterparts, low power density is a challenge that engine designers needs to overcome. And because hydrogen wants to burn pretty hot, that could actually lead to NOx emissions. Now, this is more prevalent in DI engines, and if you have high NOxes, then you would want to think about after treatment as well to reduce that NOx emissions. Another challenge is there might be a need for new turbocharger designs when it comes to specifically lean burn ICEs, because with lean burn, your temperatures at the turbines are low, so you have low energy available at the turbine, but but you need higher energy at the compressor to bring all of that hydrogen plus air into the engine. So that's a challenge that the engine designers need to think about as well. Now, moving on with more challenges when we use hydrogen as a fuel. So the reduced combustion stability and increased fire risk due to wider flammability range. So as everyone knows, like hydrogen flammability range is pretty wide. And their flame speed is quite high compared to typical fuels like gasoline, natural gas. And hydrogen wants to transition to detonation very fast compared to other fuels. And also their quenching distances are pretty small, which means like now we need to think about smaller tight tolerances when it comes to crevices in the engine where we don't want the flame to go in. Another aspect is like hotspots due to like higher flame temperatures. This can lead to undesirable pre-knock, pre-ignition and engine knock. The video actually shows the crankcase windage simulation. This simulation is not showing hydrogen, but with hydrogen, it could actually leak through the piston rings and get into the crankcase, which actually poses a explosion or fire hazard. So that's also something to think about. Hydrogen direct injection is like normally happening at like very high speeds. So you'll have like supersonic gas jets. So you would want to design to have those supersonic gas jets in your engine. And some of the micromixers in gas turbines could have really complex flow fields and significant unsteadiness that the designers needs to consider. Now let's look at with all of these challenges, how can actually Converge help in mitigating these challenges. Let's first look at flame flashback. Flame arrestors are a device that you would actually have in your intake port in a hydrogen engine where you have fuel coming in from the intake as well. Now, there are certain simulation challenges associated with modeling a flame arrestor. The flame arrestor channels are extremely small. Resolving the flow and heat transfer in smaller channels can be really expensive. Now, flame quenching is happening due to heat transfer, wall heat transfer. So you need to model your wall heat transfer inside these thin channels very accurately, and that can be expensive. Then if there are like multiple fuels, so if you bring in one fuel from the intake and then you direct inject hydrogen or vice versa, you need to have fuel chemistry modeled from multiple like fuels, and your combustion model that you use in CFD needs to be able to account for that too. Now it's all of these like challenges can be like mitigated through Converge with its autonomous meshing. You don't have to mesh at all, even though like these channels are pretty small. You don't have to mesh, and we can handle the mixing through turbulence modeling from LES to RANs. Conjugate heat transfer is an important feature to have when you are thinking of like small channels, heat transfer through the metals. And adaptive mesh refinement can resolve flame thicknesses, and specifically with hydrogen, we know the flame thicknesses are smaller than their other fuel counterparts. So adaptive mesh refinement does a pretty good job. Availability of dual fuel combustion mechanisms is also pretty important to have. Now, I'm going to show you two videos on this slide. So if you have a flame arrestor, as you can see, these like 3 channels, I'm only showing 3 channels of a flame arrestor, and if you'll see a flame is initiated on the right hand side and it will keep on repeatedly coming back to the flame arrestor. The goal of this is to see the flame arrestor walls, would they heat up when they are repeatedly hit with flame flashback, and if so, would the flame arrestor stop arresting the flame? So in the left hand side video, you could see the flame starts from the right hand side. It does not go to the left hand side. That means the flame arrestor is doing its job. you can't see here very clearly because the channel thicknesses are pretty small, but there is a solid cells model, conjugate heat transfers model. So little by little, these channel walls are getting heated up. Now, on the right-hand side, the video on the right-hand side shows when the channels heat up and attain a high temperature of, like, let's say 1200 K, you can see the flame would actually escape onto the left-hand side, which shows there is, if the metal is too hot, the flame arrestor will stop performing effectively. And those are like some of the design decisions that designers will have to do, and you can actually use Converge in similar simulations to model flame arrestors very accurately. So this slide actually shows flame flashback modeling in gas turbine engines. This was done in 2022. Again, this is the video that I showed before. This is methane and hydrogen air flame. Under certain conditions, you could see the flame actually goes back towards the swirler. Now, coming back again to hydrogen ICEs, if you have a DI, high pressure direct injection IC engine, the gas injection velocities can be sonic or even supersonic. And you need to be able to like model that accurately to get the penetration right. And if you don't get the penetration right, the mixing and the subsequent combustion will be off. Now, this kind of like modeling requires finer computational cells and finer time steps. What this means is like increased computational cost. But with Converge, you have access to all the necessary pieces to do this kind of like simulation very accurately. We have a density-based solver which can simulate like compressible flows accurately, supersonic inflow boundary conditions from total energy solver to time steps limited by convection CFL numbers, so you can actually have finer time steps. And moreover, like the solver is cell-based load balanced, so even if you have like 20-30 million cells, you could actually throw in thousands of like computers and get a very good speed up. Let's look at some work that has been done with DI engines with Converge. I'm showing like two works, like the work shown, the paper shown on the right-hand side that was published last year is from partnership with like Ferrari. And then on the left-hand side, Volvo Group and then Kaust from Saudi Arabia. They did also use Converge to model hydrogen DI engines. And the testimonial that you can see in the middle is from Dr. Amar Avdik from Daimler Trucks. He says, like I quote, "We are able to predict hydrogen combustion, both PFI and DI, quite well with Converge tested in the frame of our research project." So you could see OEMs are using Converge for hydrogen DI engines very effectively. This work was published last year. This is a PFI hydrogen engine where we simulated like 5 operating points. I'm showing here just 3 of them, a low load, a mid load, and a high load case. And without any case-by-case tuning, with chemical mechanisms generated like in-house, we are able to like, you know, get really good results with PFI hydrogen. Now, so where do we get this like in-house chemistry? It comes from C3 consortium. C3 stands for Computational Chemistry Consortium. That is, they actually like, you know, we have validated mechanisms using combustion vessel and engine data. So there are many participants in here: Convergent Science, industry, academia, and Department of Energy national laboratories, as you can see on the screen. This is actually an open mechanism, like has about like 3,000 plus species, has about 42 field chemistry in it, and we have the capability of extracting component chemistry as we want. And with this capability, we can very easily generate multi-field chemical mechanisms. And there's going to be a webinar on this in August. I invite you to attend that and learn more about the C3 consortium. For hydrogen chemistry extracted from the C3 mechanism, you can see the validity ranges, laminar flame speed to ignition delay. There's different experiments being done, and they're all validated and published. Now let's talk about hydrogen leakage and self-ignition. So this work was done by our colleagues from our European office. Now they actually took, if you can see my cursor, this is trying to simulate if hydrogen leaks from a high pressure tank, would it actually ignite? Ignition happens due to two main phenomena in a case like this: heating due to shock waves and viscous heating near the wall. So the simulation challenge in this is you need really fine mesh resolutions to resolve the flame thicknesses and the thickness of the hole that you have probably like created in the tank. Now the solution with Converge is with AMR. You can use to resolve shock waves and self-ignition. You can have AMR with respect to density, to pressure, to temperature and velocity. You can use inlaid mesh to resolve the boundary layer inside that gap or the hole that the tank has. Detailed chemistry can be used to capture self-ignition, and we can have LES turbulence modeling to resolve the flow. And as you can see here, when the pressure is low, the pressure in the chamber is low at 64 atmosphere, you don't get a flame, whereas like if the pressure in the chamber is high at 96 atmospheres, you get ignition. And which is one thing which is really interesting to note in this study is we saw that the self-ignition happens first near the walls due to viscous heating, and then it propagated to the center of the tube. So the viscous heating came first, and you need really fine mesh resolution to capture that. And with Converge, you can do studies like this. People use Converge to simulate rotating detonation engines or RDEs with hydrogen. This work is by Purdue University, where they actually used Converge to simulate different operating points. So there are two cases that corresponds to different mass flow rates. And at one mass flow rate, you have one detonation wave, and in the other, you have two detonation waves. And we were able to, with Converge, we were able to capture those physics very accurately. In May this year, we have a webinar on rotating detonation engines, and I invite you all to attend that and learn more about how you can use Converge for RDE modeling. Now, this slide actually shows you how Converge can be used to model hydrogen burners. The challenges here are the turbulence and chemistry needs to be resolved in high resolution to capture the correct flame position. Now, in this study, we have actually modeled two set of like cases where the one is an attached flame, and then the other one is a lifted flame. And we could see with Converge features like detailed chemistry to LES models to density-based solvers, we were able to match not only the flame shape and the structure, but the NOx predictions, the emissions predictions also very accurately. L stands for lifted flame, A stands for attached flame, and we are getting the trend and the magnitudes also pretty closely. This slide talks about how Converge can be used to model hydrogen rockets, gaseous hydrogen rockets. Now, this study specifically uses experimental data from this NASA Marshall Space Flight Center, and with Converge capabilities like temperature-based AMR to detailed chemistry to LES, you can do very accurate rocket engine simulations. Now, to summarize what we talked about, at the start of the webinar, at the start of my presentation, we talked about there are some challenges with hydrogen as a fuel. So everyone wants to use hydrogen as a fuel, but then there are certain challenges. Like there's high computational cost involved because of certain properties of hydrogen, like wider flammability range. It has higher flame speeds. It wants to transition to detonation and burn really fast, really quickly. And it has small quenching distances. What that means is your gap sizes that you don't want the flame to go needs to be now much smaller. And it requires certain specialized models and capabilities in your CFD code, like preferential species diffusion. What it means is you need to account for binary molecular diffusion. Your code should be able to capture and resolve shock waves. And then the detailed chemistry solver needs to be able to capture things like lean blow off in gas turbines, dual fuel combustion, emissions modeling, deflagration, detonation, transition, and flame flashback. So those are really complex physical phenomena, and the code that you use should be able to handle that, so you can model these physics problems very accurately. Now, then at the second part of my talk, I showed examples and publications on how Converge can be used to mitigate some of these issues that you face or challenges that you face. One of the things is autonomous meshing. So you do not have to mesh at all with Converge. That actually takes out the bottleneck of, like, when you have really tiny channels, or like when you have complex geometry, the autonomous meshing comes really handy. Adaptive mesh refinement, it can be used to resolve the important flow and combustion features automatically. The combustion solver and the CFD solver paralyzes like really well. Now, finally, I want to point out that we have worldwide collaborations, partnerships, and involvements with cutting-edge hydrogen combustion research. Only this past year of 2023, we had more than 30 known publications just for hydrogen combustion with Converge. So that actually shows that how much work we have been doing and our partners are doing with Converge. Now, that's the end of my talk. Now, Adam Klingbeil from Wabtec would take over and talk about his part of the webinar. Over to you, Adam.
Thanks, Sameera. Okay, I believe you can see my presentation now.
Yes, Adam.
So today I'm going to be presenting CFD analysis of a large bore hydrogen diesel dual fuel engine. I want to acknowledge the contributors to this work that are listed here below. I'm more of a receiver of a lot of the CFD analysis than I am a creator. So I don't actually do most of the CFD analysis, and it's really these people listed in the presentation next to my name that have done a lot of the work. And in particular, I want to call out Patrick O'Donnell, who's done the lion's share of the CFD work that I'll be talking about today. My background is really in experimental work, and so the question might be, why am I giving this presentation about CFD analysis? And my goal here today is not to teach you much about how to do CFD analysis. I'll leave that to Sameera or maybe Patrick. But my goal is to talk a little bit about how we use the CFD results that we get from the modeling. And then I just want to talk a little bit about Wabtec in general. For those of you who don't know what Wabtec does or what we make, Wabtec makes large equipment related to primarily locomotives. So we make locomotive engines, we might make locomotive service equipment. We also make other large engines that go into marine applications like tugboats and ferries, and we make large engines that go into power generation. So for those of you that are maybe in the on-highway market, our engines are a little bit bigger than what you might be typically used to. So I'll talk a little bit about this cooperation that we have going on between Argonne and Convergent Science and Wabtec. This is a multi-year cooperative research and development agreement where we're looking at using low net carbon fuels such as hydrogen, potentially methanol or ammonia in our engines, with the objective of reducing greenhouse gas emissions coming from our engines. So we're looking at multiple technologies in terms of the fuel system. What I'll be presenting here will be representative of a port injection hydrogen system that is ignited by the direct injected diesel fuel. But in the future, we're also looking at direct injection of the low carbon fuels. And this work is sponsored by the Department of Energy, so I want to acknowledge their support in all of this. Just in general, this project has been going on for a little bit more than a year. Last year, we had a lot of good accomplishments around modeling the Tier 3 dual fuel engine. Tier 3 is one of our current platforms that is out on the rails right now, and there's a lot of those engines in service. So it's something that we see potentially accepting a retrofit kit where you could convert a diesel engine to a hydrogen/diesel dual fuel engine. And we've been looking at things like different compression ratios, different injection timings, and different manifold air temperatures to better understand as we bring hydrogen into the combustion system, what are the impacts on the performance of the combustion system. And I'll talk more about that in the upcoming slides. So for those of you that are maybe less familiar with the locomotive industry in general and maybe some of the challenges associated with locomotives, there's a few details I wanted to call out just to set the stage about, maybe how things are a little bit different with locomotives compared to on-road. Locomotives operate in some pretty severe environments. They experience pretty high shock loads. When trains are coupling, you've got essentially a 400,000-pound vehicle driving into a stationary 400,000-pound or more vehicle, and when they smash into each other, that's basically the train coupling together. So that can be a pretty shocking environment, and it creates challenges for some of the hardware that's put on the locomotive. Another challenging condition for locomotives is tunnel operation. Some of the tunnels that go through the mountains in North America are unventilated, and the consists of trains and cars that go through those tunnels can build up a hot exhaust inside the tunnel. So when the first locomotive in the consist goes through that tunnel, it experiences relatively fresh air, but it's dumping all of the exhaust, it's dumping all of its waste heat into whatever is remaining inside that tunnel. When the second locomotive in that consist comes through behind it, it's now ingesting exhaust and waste heat from the first one. So it can very quickly run into challenges with low oxygen levels and difficulties with rejecting heat. So that's another challenging condition that locomotives experience, and we need to understand how to deal with it. In general, locomotives operate at a pretty high load factor. They could operate at full power up to 17% of the time, which is pretty significant. And then in terms of their life, locomotives can operate over 30 years. In fact, if we look at this chart showing the relative number of locomotives that are in the installed base, that are 2005 and later versus pre-2005, you can see there's a significant number of locomotives that are pre-2005. And the reason for that is pretty simple. Locomotives are really expensive. So replacing one isn't something that you want to do very frequently. In the same way that we don't tear down our houses every 10 years and replace it with a new house because it's more efficient or it looks better. We don't replace locomotives that often. Instead, we look for ways to improve the locomotives that are already in service. So retrofit kits that can offer improved fuel efficiency, offer lower emissions, offer potentially more capability are attractive for that very large installed base where the customer wants to keep using the asset they've already invested in. So the work that I'm presenting here is based on our NextFuel dual fuel platform. The NextFuel dual fuel platform is a dual fuel retrofit kit for our Tier 3 locomotive engines. So the Tier 3 locomotive engines are typically a diesel electric locomotive, and then we've developed a natural gas diesel dual fuel retrofit kit called NextFuel that we can retrofit into those locomotives, and we've got some of those in service in North America. So the work that we're doing here, the analysis that I'll be presenting, is based on that same design, but instead of using natural gas, we'll be using hydrogen as the gaseous fuel. And then in the analysis, we assume diesel fuel is the liquid fuel. Just a few details are listed here about the engine. It is 375 horsepower per cylinder. The cylinder is a 250 millimeter bore and 320 millimeter stroke, which gives us 15.7 liters per cylinder displacement. This slide gives you some details about the computational setup, all the different submodels that were used in the case of the analysis. And here's some pictures about some different grids that we evaluated in the early part of this project. And the table below here shows you basically as we go from grid 0 on the left to grid 5 on the right, we're going to more and more refined grids. And we did a study to try to understand, as we refine the grid more and more, where do we no longer become sensitive to that mesh refinement. And we settled on grid 1 as providing us pretty good computational performance and also pretty good grid insensitivity. So the data that I'm presenting here for the rest of the presentation will be based on this grid 1. So I'll jump now into some results. This plot is showing cylinder pressure and heat release rates for 4 different simulated conditions. Basically, as a starting point, we ran 50% substitution rate by energy. So the hydrogen is port injected, it's premixed with the air, and then the diesel is direct injected, and that diesel fuel, when it's injected at typical diesel injection times, ignites and then also ignites the hydrogen air mixture. And so for this particular case, we're running 50% substitution by energy. Like I said, the engine was a 12 compression ratio and 118 degree manifold temperature. So what we're looking at trying to understand is if we change, for example, the manifold temperature, if we change the compression ratio, how does it impact the combustion? How does it impact things like maybe fast combustion or knock? And how does it impact efficiency and emissions? So the 4 cases simulated here are 4 different injection timings for the diesel injection event. So you can basically look at that as 4 different start of combustions. And if we look at the heat release rate, all 4 of them are very diesel-like in nature. We get sort of a premixed spike in the heat release early on, and then kind of this diffusion burn that looks very much like a typical diesel combustion event. And that, I guess, for us is maybe the desirable type of combustion event because we know how to control it. It behaves the same way as the diesel engine. So in an engine that may be running dual fuel mode on one day and 100% diesel mode on a different day, a combustion event that behaves similarly in either mode would be attractive. Now, if I go to the next slide, we can compare what it looks like for, I'll say, higher compression temperatures. In this case, the compression ratio is 15 and the manifold temperature was 143 degrees Fahrenheit. So higher manifold temperature and higher compression ratio, both together serving to give us a higher overall compressed gas temperature even before ignition started. And we also ran 3 different combustion timings here. And you can see for the latest combustion timing in orange, the heat release rate is relatively slow, but looks kind of like a diesel combustion event. But then as we go to the earlier timings, we notice that the heat release speeds up, but then we have kind of this acceleration near the end of the combustion event. And for the earliest timing, we see it really exponentially accelerates at some point. And that kind of combustion is something that we're happy to understand in CFD, and will probably be something we want to avoid in the engine because of the rates of cylinder pressure rise, and potentially the peak cylinder pressure may be higher than would be sustainable in a product. So enough talking about one-dimensional data. I guess I'd like to show a little bit of some CFD results. I think everybody likes to see these types of pictures. And so what I'm looking at here is basically temperature profiles from the previous slide conditions, where we've got 50% substitution rate, we've got the higher compression ratio of 15 and the higher manifold temperature of 143. And we have 3 different start of injection timings. So -4 degrees, this is the earliest timing, -2 degrees, and then +2 degrees. And so the snapshot that I took in time is 14 degrees after the start of ignition, or start of injection, sorry. So these are each at slightly different actual engine timings, but they're all 14 degrees after start of injection. And in this case, for this particular snapshot in time, when we look at the temperature profiles, they all look fairly similar. We can see the diesel fuel plume here in the center because we've got 50% diesel fuel in there, so there's a fair amount of energy being released from the diesel fuel. But then we can see these areas around the plume where the flame is propagating out into that premixed hydrogen-air mixture. So it's moving beyond the diesel plume. And that's what we would expect. As the diesel is injected, it ignites. Once it ignites, it creates a flame that can propagate into the hydrogen and air mixture. And there are some minor differences between these 3, but really nothing drastic. So 14 degrees after start of injection, they all look fairly similar. If I go to the next slide, we start to see some differences. This is 17 degrees after start of injection. So it's 3 degrees later. And now for the latest injection timing, we can see that flame is propagating into the hydrogen air mixture. It's moving along, but not real fast. And then as we go up, these are for earlier, this is for the middle timing, we can see that flame has propagated further into the hydrogen air mixture. And then for the earliest timing, it's propagated further yet. And if I take one more, this is just 1 degree later. Now we can see for the earliest injection timing, most of the hydrogen has been consumed at this point. We can see the flame has propagated up to just the cold surfaces, basically. There's not much else that can be consumed. And that's what we saw in the heat release as well. right, we saw that the heat release started off, and then as we got to this 17 or 18 degrees after start of injection, the heat release took off, and that's because this hydrogen all started to burn very quickly, which we can see in this image. While with the other two injection timings, you can see that flame is still propagating. It's taking its time to digest the remaining hydrogen fuel. So we also did a study looking at different compression ratios and different manifold temperatures. So this plot just shows you the cylinder pressure for 4 different combinations. In red, we've got a 12 compression ratio. The solid line is the lower manifold temperature of 118 degrees Fahrenheit, and the dashed line is 143 degrees Fahrenheit. And then in black, we've got the higher compression ratio of 15, again with the 118 and the 143 degrees manifold temperatures. So in general, what we would expect is the low compression ratio and low manifold temperature case in the solid red line has the lowest gas temperature prior to and during combustion. And then the high compression ratio, high manifold temperature case, which is the dashed black line, has the highest compressed gas temperature before and during combustion. And then what we see from all of this is 3 of the 4 cases that we're looking at here show relatively controlled combustion. And then the 4th one, the high compressed temperature case, again, it very rapidly increases in cylinder pressure because the combustion event is accelerating quickly. So I'm showing here the heat release rate for those same 4 conditions. And again, for 3 of the 4 conditions where the cylinder pressure was under control, we also see the heat release rate is relatively smooth and I would say diesel-like, even though this is a dual fuel operating condition. But then for the 4th case in black, again, we see that heat release take off very quickly and shoots up very high, likely because it's consuming all of that hydrogen very quickly. So I've got some snapshots here at these points in time, which I'll show in the next 3 slides, and we can see how that fuel is consumed as we go through time. So in the top left, again, we've got the lowest compressed gas temperature because it's got a low compression ratio and a low manifold temperature. And then the top right is the next highest compressed gas temperature with a higher manifold temperature. And then here we've got the next warmest one with the higher compression ratio and the low temperature. And then in the bottom right, we've got the hottest one that had started with the high compression ratio and the high manifold temperature. And this is the one where we saw the cylinder pressure accelerate and we saw the heat release accelerate very quickly. So we can take a look at how this evolves over time for these 4 different cases. Again, early on in the cycle, this is 8 degrees after top dead center. The combustion profiles all look fairly similar. For the coldest case, you can see there's not as much propagation of the flame into the pre-mixed hydrogen and air mixture. It's mostly the diesel plume that's burning. And then for the hottest case, you can see there is more propagation of the flame into that pre-mixed mixture. But in general, I'd say these 3 all behave relatively similar at this point in time. If I go to the next time step here, this is 12 degrees after top dead center. Things are marching along a little bit more. This cold condition, we see that the combustion is now starting to spread into the main combustion chamber beyond the plumes, not as much as the other ones. And then for the hottest case, we see that it is spreading a little bit faster than the other ones. So we start to see this one separate itself from the colder counterparts in the other 3 boxes. And then lastly, this is 15 degrees after top dead center. This is right around the peak of the heat release for that hottest condition. And you can see we've essentially consumed most of the hydrogen at this point. So this is a condition where the combustion rate has accelerated very rapidly because the flame is moving so quickly to consume all of that hydrogen, and it at some point feeds itself and continues to accelerate exponentially until that hydrogen is consumed. So these types of conditions will be things that we want to explore in testing, but we probably want to avoid in practical operation because we would have concerns about how that impacts the reliability of the engine in the long term. I wanted to talk about one other topic that we've been exploring in CFD, and that's backfire evaluation. So one concern that we have with hydrogen dual fuel when we're injecting the hydrogen gas into the intake port is the concern about having backfire, where when the intake valve opens and the hydrogen and air begin to get ingested into the cylinder, if that hydrogen touches some hot exhaust gas or touches a hot surface, could it ignite and then feed back into the intake manifold and then have all that fuel burn in the intake manifold, potentially in a catastrophic way? And so we started looking at this on this project as well. I'll show you a little bit of information that we've got so far, but this is a work in progress, so we've only just begun on this particular topic. So the way this was modeled is we ran a CFD evaluation of the intake runner and the cylinder, so that whole entire volume, with combustion turned on throughout the cycle, so that we could see if we get combustion, not only do we get combustion in the cylinder, but do we get combustion in the intake manifold. This is a pretty expensive simulation because you have to run it 720 degrees, but not only that, we ran it multiple cycles to set up a steady state condition, and then you have to run it with the combustion chemistry turned on for the entire cycle, not just during the closed portion of the cycle, which is a common method of running the combustion CFD. So when we did this, we simulated the port injection like we would have in our engine, and we simulated the engine breathing events. And then we evaluated from the CFD results whether or not we thought we could see ignition caused by, for example, the exhaust gases, the exhaust residuals in cylinder that may be propagated backwards into the intake manifold during valve overlap. So on the left, I've got a plot of the hydrogen mass in the intake manifold. And so basically what we're seeing here is this is the start of hydrogen injection. And then it kind of fluctuates because the hydrogen injection is a non-steady process, but also the engine is breathing at this time. So it's pulling the hydrogen air mixture in during part of this. And so the concentration is fluctuating. And then on the right, we've got an image of the intake manifold temperature. So there's three lines plotted on this graph. The top line is the maximum temperature in the intake manifold, and the bottom dashed line is the minimum, and then the solid line is the average temperature. And so if we just look at the average temperature in the intake manifold, we would think that probably there's no combustion going on in the intake manifold, and probably nothing of concern really to speak about. If we look at the maximum temperature, we do see this spike early on. This is during that part of the time when the intake valve just opened. And so that's something that we would want to look at and ask, okay, does this spike in temperature represent combustion? And if so, is it a significant concern? And I can't answer that question because we're still looking into the results, but we believe at this point, this just represents some of the exhaust residuals actually just bleeding back into the intake manifold. But because it doesn't propagate into the main mixture of the intake manifold, we don't see the average temperature change significantly during that time. So this is one condition that we looked at. but this is just the beginning of a backfire study. So we'll continue looking into this, trying to understand as we change operating conditions, do the results change, and can we simulate a backfire condition if, for example, we change the timing of the hydrogen injection and change the engine conditions in such a way that more hot gas can make contact with the hydrogen air mixture. So this is still a work in progress, but again, I just wanted to touch on it and show everyone some of the interesting things that we're using CFD to try to understand about this engine platform. So future work that we have planned in this, refining that backfire analysis and going into more depth, that's one thing that we want to be exploring in the future. Comparing results to experimental data. Right now, we don't really have experimental data for this engine, but we'll get it later this year. So once we do, then we'll do some comparisons to be able to validate our CFD and potentially identify any errors with the CFD that we need to refine our models. And then we'll also be evaluating direct injection concepts as well. Everything presented here was port injection, but port injection for the hydrogen. But in the future, we'll also be exploring direct injection for the hydrogen fuel. So with that, I'll end my presentation, and I think we can move on to the question and answer portion. Thank you.
Great, thank you, Adam, and thank you, Sameera. These were fantastic presentations. So we really appreciate both of you taking the time to not only share today, but also the preparation that went into that. We'd like to just share a couple things with you as we go into the Q&A portion. If you'd like to receive additional information about Converge CFD software from Convergent Science, you can get that through signing up using the QR code on the left and get news and events that will send you things like our newsletter just to keep you updated on what's happening with Converge CFD. If you'd like additional information on how you can use Converge CFD, you can contact us through using the QR code on the right-hand side. So if you scan that code, you'll be contacted by a representative from Convergent Science. And then finally, we'd like to invite you to not only join us for any of our upcoming webinars that we have scheduled for 2024, but by clicking on this QR code, you can actually have access to our library from previous webinars as well. So we'd encourage you to scan this code, go and check out our library of webinars and join us for future webinars.